Okay, how do you guys find the regression from last time? Is it okay? Or okay, you understand more or less about regressions, right? Okay, so today we're gonna go through regression in more in depth. I'm gonna talk about what's the assumptions and how to make a better regression model. Okay. So let's go back to the previous example we had. That's the Hong Kong Kowloon data, and our goal is to predict the price and predict whether or not it's expensive. Okay. And just a recap, the way to do regressions is to split it to training set and testing sets, and that's how to do it. You just sort the columns by the question marks. Okay. And then you created your train X and train Y. Sorry. Oops. Hold on. Let's read. Okay.
What's the meaning of the AS type?
The S type integer means just converting everything to an integer instead of a float. Okay, let me see why this line doesn't work. Okay, this should work. Yeah, I'll define it to train X again, and hopefully this will work. Okay, it works. Okay, train X, and then also we have to define unknown features. That is for us to project our regression line. So we have unknown X as well. And now we've fit the model by instantiating the linear regression line, and then we fit it by train X and train Y. And then we test it on the unknown features to see if we got the right price. Okay, and last time we got 5,033 and 153 for the cheaper houses. And do you remember how to get the coefficients? Anyone? Sorry?
To write down the form.
Yeah, just and how to get the coefficient from the model. Yeah, .coef underscore. So just lm.coef underscore. Oops, lm is not defined. Yeah, I call it regression this time. Regret. Oops. REGR. Okay, that's how you get the coefficients.
What's the difference between LM and REGR?
It's just the naming of how you name your model. It doesn't matter. If you put LM in here, and basically from now on your model is called LM. Okay, you can name it whatever way you want. If you do it LM, it still works. Okay. Okay, and if you plot out the coefficients, sorry, import numpy as np. Okay, if you import the coefficients, you can see the coefficient for each factor. And okay, how do you remember what coefficient really means? If it's a negative value, what does it mean? The coefficients. It means negatively correlated. Okay, if it's positive, it means positively correlated. And what the magnitude really mean on a regression coefficient? The magnitude means 3.13 for size. What does it really mean?
Size change by 1 unit and price by increase
That by 3 units. Yeah, that's it. So because our y, our dependent variable, is price, the coefficient actually means if the size changed by 1 unit, the price will increase by 3 units. Okay. And we also have something called the score of fit, which is the R square. Anyone remember what R square actually means? So you can interpret it as how good your model fits onto the model. Okay. If it's very close to 1, it means your model is doing quite well. If it's closer to 0, it means you probably have to add more variables to make it better. Okay. Oops. Train Y is not defined. Okay. Anyway, and this is how you plot the regression line. I'll see why train X is not defined. Train X. Hold on. Train X. Okay, never mind. Supposedly this code should help you to plot a line of fit of the predicted line versus the actual line. Okay, but I'll try to fix this later on. So now we have exercise for you. Exercise 7.0.0. You're given a data set with the body height and weight, and you have to do a prediction using linear regressions. Okay. The first part is just figure out what's your train X, train Y, and the unknown X, and then you define the model, fit the model, and try to see if you can do predictions. Okay. If you want to copy the code, just feel free to copy what's on top. everyone done with the first part? Train X, train Y, unknown X. Okay. So shouldn't be too hard. Train X. What's train X? Which column do we want for train X? The first two. Okay. And which row do we want train X? Yeah, top 7. Okay. And how about train Y? Train Y we want the weight column. Okay. So basically train X is the data frame dot weight that's not equal to a question mark, and then you just type in all the columns you want. Okay. Train Y is very similar, but just to select the weight. And unknown X is everything in here. Okay, these 4 numbers are unknown X. Okay, and okay, how do we fit the model? Okay, we first thing we need to instantiate our empty model. Okay, we just do linear model dot linear regression, and then we click. And then the next thing is we just fit in the train X and train Y. So lm.fit train X and then train Y, and then equals to lm. Okay, now you created the model. If you just type out lm, it just shows you a regression, linear regressions. You can also input some parameters like do you want to intercepts, or if you know how to do parallel computing, you can do more than 1 jobs. So let's say if you are handling a very big dataset and you have 8 cores in your CPU, okay, you can set n jobs equals 7, and then it will be 7 times faster. Okay. Okay, and then to predict something, basically you want to predict the question marks. And then how to do predictions is you make use of the features of the unknown value. And basically in this case, the first column is height, second column is sex. So it's just saying if a person is 160 cm tall and she's a girl, what's gonna be the weight? Okay. So to do a prediction, just do lm.predict and then put in your unknown features, and then it will just output the 2 predictions that you were expected. Okay. Alright, and then the next question is to know the goodness of fit, like how well your model do. And to come up with the score, you need 2 inputs. One is to train X and one is to train Y. And any thoughts why do we need these 2 variables to come up with the score? Basically the score, it's comparing your model's performance with the actual value. Okay, so what this score actually does is it uses train X put into predicted value. So basically it does this lm.predict, and then instead of unknown X you can predict using your training data. Okay, and this is what you predict But you know the ground truth of this, right? Which is train y. Okay, and what the score does is just comparing these two values. The expected weight versus the predicted weight. Okay. Any questions? Right here. Okay. Okay, and the score is 0.93, which is quite good. Oops, sorry. And then lastly, this is how your best fit line looks like. These are the dots. Okay, this is the predicted value based on the straight line, and this is what the ground truth is. Okay, so every value that you predicted will be on the straight line. Okay. Any questions for now? Okay.
I have
Yes.
error. It says could not convert string to float.
Where do you see that error? Well, because your unknown x shouldn't contain this column. Okay, if your unknown x contains the weight columns, it will throw you an error. Okay. All right. Last time, someone asked me a question. Say, if like building model is so easy, what makes a good data scientist a good data scientist? Because every time you apply the model the same way, and it's just like 2-3 lines of code. What makes, like, how do you add value to the case? So if you go to Kaggle, okay, Kaggle is just a website that data scientists compete. And if you go onto the ranking, and let's say you go to Titanic and you click on the leaderboard, and basically they're competing for a score, and this is the score we just talked about, which is the R square. Okay, and then so they basically train. Oh, sorry. They gave you like the partial data for you to train, and then you send the model to them, and then they'll test it on the ground truth. Okay, and they'll come up with a score. Okay, you can see the top players got the perfect score, but once you scroll down, you see the score drops quite dramatically. And you might wonder, like, if they all do linear regressions, how can they have different scores? And the reason for this is because one, they don't use the same model, and two, they put in different eggs. They use different train eggs to train the model. This is so-called the feature selections and also the feature engineering. So let's say if you go back, if you go back to height and sex, okay, like everyone can use these two columns to do regressions. But let's say, okay, height and sex, there might be a correlations. Okay, if we take the let's say the correlations between them and add one more columns. Okay, and that columns contains a new value based on these two columns. Now you're generating a new data sets, and that might help you to predict value in the future. And this is so-called feature engineering. Or let's say go back to my data sets. So I have something called shot on box for the football data, which is actually very similar to shots on target. So if you play football, you have the shots, and you can be on target outside of the box or inside of the box, but they are essentially the same thing. Okay, if you add two very similar things into your data, you might decrease your prediction power. So what a good data scientist has to do is you have to pick out some columns that are correlated to each other. And you can also create new column based on your domain knowledge. Okay. And that is so-called that is the real value adding to gives you a high score. Okay.
So you're saying being a better data analyst, we need to choose the right data and to take out data who each correlated to each other.
Yeah, basically you have to pick your data set smartly. Okay, it doesn't have to be pick out the correlated one. You can think of some new data to add in to improve your model. Okay, or you can choose an even better model that better fits your data. Okay, because different models apply better on different situations. Yes.
So like when you pick this kind of stuff, is it all based on experience, or is there some way to like see a model and then try to improve it over and over?
Actually, if you know programming, you should be able to think of a very quick way to test which model is the best.
But like, I know that you can like try different models and use the data.
Yes.
But like the problem is maybe like eventually you will find a model that fits the test data very well, but
yes.
that may not be like the actual like good model for all the data.
Yeah, that's a very good point. So your point is, if you overfit your data, it works very well in your data sets, but if you put in something that is outside of your data set, it will do very badly.
So in short, I think his question is how to strike a balance between overfitting and choosing the good model that fits your data well.
Okay. Actually, there's a technique that is called cross-validation. Cross-validation, which I'm going to talk about soon, but we can talk about it now. Okay, if you scroll down to 7.0.5, okay, there's a technique so-called cross-validations. Let's say you have 100 rows of data. Okay. If you train your model using the entire 100 rows, you're gonna build a very good model, but you can't really test it. So what cross-validation really means is you train it on 90% of your data sets, test it on the remaining 10, and after that you train it on a different combination of 90% and test it on the remaining 10. And if you have 100 row and you split it by 10, you can do a 10-fold cross-validations. Okay, and if the scores you get is very consistent and it's very high, this means your model is quite generalized, and at the same time your data is quite generalized as well. Okay, but let's say if you test it for 10 folds and the score fluctuates a lot, this means either your data is not big enough or your data is biased. Like some part of the data is very different from another part of the data, or basically you select the wrong variables. Okay, And I hope that answers your questions for how generalized the data can be. And back to your first questions, for choosing model, you can actually try every combinations of model. Okay, you can list out like 10 models and you can try them all and see which one gives you the highest score. Okay, but again, if you don't have any domain knowledge with the model, you can't really explain why this model performs better than the other one. Okay. Sorry. Okay, let's get a little bit more in depth with regressions. We have different types of regressions. So we have the simplest linear regressions, that is plotting a straight line. What if your like the relationship between your dependent variable and independent variables is not linear? Okay, let's say it's a curve. Okay, so what would you do in that case? Like, let's say, can't think of a good example. Let's say, okay, I'll open an Excel. Okay, this is a good example. Oops. Okay, watch and price. Okay, there's some products that, let's say for watch or for cars, if you improve your specs, the price increase exponentially. Okay, let's say you get entry-level cars like a Toyota, it might cost you 100K. Okay, like car. And let's say this is like model 2. And then once you increase your model, it can be model 3, model 4, model 5. But the price will increase exponentially. Maybe at first increase by half, and then the next one is 400K, and then the next one is 800K. Okay, and this is your model type. Okay, now you can see the type, like the model number increase linearly, while your price increase exponentially. Okay, it's not really a straight line. Well, let's say I put 16. Okay, in this case, what can you do? If you fit it to a linear model, it's gonna plot a very weird straight line. Okay. So again, this is a feature engineering skills. You can manually transform this price by a square root. Okay. Just manually transform it to a different order of magnitude. Or you can do you can do like polynomial regressions, which is having one of the eggs as a square or a cube that solves the problem. Okay. And in a regression, we also have something called a multiple linear regression.
Regarding the converting to a square root and doing it.
Yes.
And then just using the polynomial. Is there any benefit of either form, or is it both the same?
So I would say if you have domain knowledge, when you do your exploratory data sets, you see there's such quadratic relationship. If you eyeball it and see it, you don't have to waste time to try all the polynomial. because when you try the polynomial way, every time it takes you like a very long time to load, and you have to try out to see which degree is the best.
So polynomial you have to put the degree as well.
Yeah.
It's not gonna degree dot.
Yeah, it won't. We also have something called a logistic regressions. Anyone heard of it? So logistic regression, it's instead of predicting the magnitude, it helps you to classify. Okay, and the way it classifies two things is basically plotting a line on a graph, so it separates two boundaries. Okay, if you visualize it, okay, like if you visualize this graph, okay, it's sort of like split the square into two halves, right? And whenever you do a classification, what you're doing is actually drawing the boundary on the graph. So what logistic regression does is basically draw the boundary using a straight line. Okay, so you're not predicting a magnitude, but predicting two groups. Okay. Okay. Why do we need to use regressions? In what situation is regression better? Any thoughts? Regression is actually very good at telling you the relationship. Okay, if we use the more advanced data science approach, you put things into a black box and compress the dimensions. And once you do that, you lost all the chance to explain to, let's say, to your colleagues, to your client, what's going on. Why do we have such results? In regression, we can discover the pattern and vector one by one because we have the coefficients. Okay, and we can also plot out the graph fairly easily. So usually the first model for every data science problem is linear regressions because you can find out the relationship quite easily. And if you don't really understand the formula, what regression does is just like you have an intercept, these are the coefficients, these are the moving parts, and so on. And at last, you will have error terms. And let's say go back to the house price example. Basically, the entire functions is just an intercept plus coefficient 1 times age plus coefficient 2 times size plus coefficient 3 times locations, etc. And what's important now is the error terms. Okay, because there are some terms that you can't explain using a straight line. And what it means by error here, it's the distance between every dots to the line. Okay. Okay, now what's interesting is how do you interpret the error? Okay. Anyone heard of this term? Heteroscedasticity. Okay. Usually you learn this term if you are a stats major. So okay, it's start to go quite philosophical because heteroscedasticity means your distribution of the error. Okay, let's say if your error looks like this, what does it really tell you? It actually means your error is bigger if the magnitude is bigger, and your error is smaller if the magnitude is smaller. So what does that actually mean? That actually means you're missing a variable. Because if your model is perfect, this shouldn't happen. Your error should be consistent throughout the scale. Okay. Does that make sense? So if you predict something, and then sometimes you predict it quite accurately, and sometimes you predict it very wrong, that actually means you're missing something. Let's say when you predict a house price, okay, let's say you predict cheaper house, you get very small errors. But when you predict a more expensive house, you got a lot of errors. That probably means you're missing a variable, like maybe locations, or maybe like the number of rooms, etc. Okay, so this is something you should avoid.
So the word issue this
Yeah.
Is the description of this phenomenon.
Yeah. If this doesn't happen, it's called homoscedasticity. Okay. Hold on. Also, there is something called multicollinearity. Okay. By looking at the word, it means your variable should not have correlations. Okay. But in reality, it is quite hard to avoid. Okay. It means let's say in this example, what a perfect model should do is the house size shouldn't be related to the house age. Okay, and the location shouldn't affect the age of the house as well. But in reality, it is very hard to avoid this sort of correlations. Okay, and if you really have heavy correlations, you can do so-called interaction terms. Basically, just create one more columns that contains both variables. You can plus them or you can just times them. Just do interaction terms. Okay.
But how does the multicollinearity affect the result of the regression?
That's a good question. So
yeah, because there are many data in which the training X are quite correlated to each other sometimes, like the stock market.
So I would say your predictive power won't be affected by much, but your explanatory power of every coefficient will be different. Because if two things move at the same directions, the magnitude of the coefficients will be divided by half. Because you're now counting two things by the same coefficients. Okay, so that coefficients will be different. Okay.
CB doesn't matter if there is this kind of situation or not.
It depends what your goal is. If you want to predict something, all you care is the perfect predictions. Then you don't need to care about such thing. But if you want to explain to your client, say, if the house age increased by 1, how much would the price increase? If you want to find that relation, then you would care about multicollinearity. Yeah.
So in this scenario, the explanatory power is compromised.
Yeah, with more variables. But also, it tends to be if you put more variables, the better you predict. Yeah. So it's the balance that you have to take. Okay, a different concepts. Do you guys need to take a break, or is that okay?
Okay.
Okay. All right. Okay, there's terms called overfitting and underfitting. Okay, it means how well your model fits on your training data. Okay, there's something called underfitting, which means your model is not really representing the pattern. Okay, while the pattern is like a curve, your model is a straight line. This means it's not saying anything. On the On a contrast, there's so-called overfitting, which means your model is trying so hard to be perfect on your training sets, while it shouldn't be generalized to a general case, like this. So it tries to fit in every single blue dots. So in this case, the result is 100%. But if you have a new red dots, it probably will be misclassified as the blue one. So the perfect example should be this. So you have some wrong predictions, but overall it generalized quite well. Okay, then this makes a good model. Yeah.
Looking at this and your Prager one for Titan, you had a number of people with prediction 1.
Yes.
Does that make their models overfitting?
Sorry, the
Kegel one, Titan.
Actually, they are not overfitting, but because the testing data is out of a sample.
Oh.
If they do it on their own training sets and get 1, and yeah, that's a different thing. So their 1 is actually using unknown data. Yeah. But I guess I don't know how can they do it, because probably they have the full list of.
Because the article that he gave us.
Yeah.
According to him, he has both data sets.
They have what?
They have both data sets.
Okay.
They have given a testing data set as well as a training data set.
I think what he meant is he just split the data set he have to train and test. But the one Kaggle used it to rank is something else. Yeah, it's out of a sample. Yeah. Okay. Any questions? Is that quite confusing or quite boring? Okay. Okay, this is an example of how you try different degrees in your regressions. So if you look at row number 15. Okay, you can type in your degrees. 1 degree means a linear, 4 degree means a quadratic. Okay. And this is how your curve would look like. Okay, if it is a quadratic relationship, if you plot a straight line, it's going to fit the data quite well. But if you use like a degree of 4, it fits in perfectly. But if you use a degree of 15, then it's just way too much. Okay. And this is the cross validations that I already talked about. Okay. And in coding, you can do cross validation quite easily. So basically, you just you just key in this library, sklearn, model selection, and cross validation predict. Okay, and the line that does cross validation is this line, line 12. So what it does is you just put your model, your data, and CV means how many times you do your fold.
What does that mean? Like how many times do you do the fold?
Okay. Okay. I'll explain it again. So for cross validations, you're basically rotating your data. So you use 90% to train and 10% to test. And what you rotate is the 10%. So you can use your 10 first 10% of your data as a testing set, and then you rotate to your next 10%, and you rotate to your next 10%, until you repeat the process for 10 times. Okay, and that's what I meant by tenfold, because you're folding it for 10 times. Okay. Does everyone understand cross-validations right here? Okay. And this is just an example of how to do cross-validations. Okay. And okay, shall we take a 10 minutes break? Okay. Okay, let's take a 10 minutes break. Okay, sure.
So about the CB, like CB equals 10, which means there are like 10 kinds of.
Yeah. Yes.
Oh, okay.
Yes. Yeah. Is Anaconda the only Python on your computer? Have you installed anything else? Because I suspect you have like 2 versions of Python. See if that's the same one. Yeah, that should be the same. Okay, let me try to search online. Yeah, I'll try to find Windows 10 XG boost.
Yeah, I cannot find the solution for XG.
Okay.
So if I have Python for under Anaconda,
Yeah.
should I uninstall the other Python?
Yeah, this is always tricky. It's not good to have two Python on your First, when you install something, Windows might decide to install on this or the other one. Yeah. So, Python 3.
I found a solution.
You found solutions. How?
There's one on. You have to download the files directly onto the computer and then use your terminal to.
Oh. Okay. Do you have the link?
Yeah.
Okay. Do you mind? Okay. Why did they make it so complicated? So you download one of this?
Yeah. And then go to the file. Then click install.
Okay.
But then you have to use the whole file.
I see. Do you have to key in the name of this?
Yeah. Unless you reach can change it.
I see. Think if there's a cleaner way of doing it.
It seems very simple.
Okay.
There are a lot of people asking the same question.
I see. Okay, I'll post out the solutions. Thank you. Maybe you can try this. Anaconda search -t Conda XG push. Let's see if we can. I'll come back. do everyone have problem with XGBoost installations, or have anyone? Okay, I'll find the solutions online and email it to you guys, because everyone uses different operating system, and I don't know. I don't know how can I find out.
I can find it online.
Sorry,
I've tried to find it.
you can't find online.
Yeah,
Right?
I tried all the way.
I see. Like for Windows users, it's actually the best to have Linux inside your window if you're using Windows 10. So actually, that's a way of that's how it should look like if you download Ubuntu into your Windows 10, and that solves basically everything. Because like once you go into DSML, you should learn how to use Linux. Although it's quite scary at first, but it shouldn't be too hard. Yeah, if you're using Mac, then yeah, it shouldn't be a problem. If you're using like the latest Mac, but if you're using the older one, that might be a problem. So okay, hold on. Okay, I'll just do one last cross-validation example. So this is an example using iris, the flower example you saw last time. And this time I'm using a model called SVC. Okay, SVM, that is the support vector machine that's doing classification. And if you load the model once, you can see a score is 0.96, a 96% accuracy. But if you want to know how the model performs generally, you can do this. Just do cross validation score, put your model in, put the train X, put the train Y, and then type in how many times you want to do your cross validations. And then below is the score. You can see the score is quite consistent. Okay, you can play around with different numbers. Okay, usually the more number you type in, usually the better will be the score. And the reason is because you use more data and test it on a very small set. Okay. So you can see a lot of 1.
So CLF is the predicted data.
Sorry, which one?
CLF.
CLF is actually the model. Just like LM or the REGR, you can just name it whatever way you like. But usually you do a CLF for a classifier. Okay. Okay, and here comes to another important concept called regularization. Okay. Okay, this is an example of overfitting. Okay, this is the real data, and you try to fit every single dots, and now your line is very curvy, and it doesn't generalize well. One way of doing it is to cut out some variables. Okay, instead of using all the variables, you delete some of them. To make it more visualized, let's say you have a lot of race car, and then you want to plot the curve of what's the average position of the car. Okay, let's say there's an accident. Okay, and then because of the accident, some of the car goes to the very far edge of the curve. Okay, if you include those cars in the average positions, the curve's gonna be different. So what you want to do is you want to eliminate those accidents. And that's quite similar to chopping out some variables that you don't want. I think this example is quite intuitive for you to understand regularizations. So you have a bunch of words that describe some pets. Okay, you have a snake called Bo, which is small and friendly, and you have a dog called Miles that is small and friendly as well. And let's say if you want the robot to classify these animals, the robot will just think of a rules like pets with up to 4 letters are enemies, as are larger dogs with names beginning with A, except the small snakes that are not enemies. Okay, because the computer will just come up with the perfect rules that separate the two things. But in contrast, you can simplify the rule and say, okay, large dogs and cats are enemies. And now you just make the model a lot cleaner and a lot more generalized to new data. Okay. And luckily, you don't have to do it manually for chopping out the extra variables. There are 2 ways called, I forgot how it calls. It's called, I think it's called Ridge. Let me search. RIDGE. Okay, Ridge and Lasso. Okay, usually, okay, if you want to know how it works, maybe I can send you some links, but even I don't really know how it works. All I know is it will select variables and cut off those that are redundant and make your model cleaner. Okay, and how you use it is just import the libraries and then call the model just like how you use the linear regressions. Oops, sorry, do it from the beginning. Okay. Yep. Sorry, let me have a look at the sets. Right, this is an example for transforming your data. So if you looked at, well, this is actually quite true for a lot of price data, which is skewed. Okay, you can see it has a longer tail, and it's not very normal like this case. Okay, what you can do if you want to do a perfect predictive model is you should put a lock on the price and transform it to a more normal shapes. Okay, if you manually do it, your model tends to perform better. Okay, because I think the rule of thumb is if you see anything that is not linear, try to make it as linear as possible. And if you see something that is not symmetrical in the plot, just try to make it more symmetrical. And then, okay, if everything works fine, you will just plot out a graph like this that plot out all the coefficients, and then it's gonna drop out the least troublesome ones. And after you run everything, it will just give you the better results. And I think in this case, I'm just comparing the XGBoost predictive power. Okay, so well, if you look at this line, it just say Lasso picked 111 and 1 variables and eliminated 177 variables. Okay, so all you care is just it cuts off a lot of variables. Okay. Alright, okay. So here I have a new concept, which is called PCA. Okay, I closed a window. Okay, PCA and LDA is so-called dimensional reductions, algo. I think I keep on repeating this. Let's say you have a data set that is very wide. You have 5,000 columns. Okay, all you do, like what the data scientist would do, is do a PCA and compress it to 4 columns. And how I did it, or how do you visualize it, is something like this. Okay, if you have a relationship like this, you can try to twist a line and make and create a new variables that is quite generalized to the general directions. Okay, if you see it rotates, you can see there's a point that the error is maximum, and there's a point the error is minimum. Okay, so what PCA does is it keeps on finding the general directions of every single dots and just create some new variables out of it. It is also an unsupervised algo, so you don't need to care. The computer will figure it out the direction itself. You shouldn't worry about LDA. Okay, I think the better way to demonstrate is to use an example. Okay, let's say I have okay, this is my X train. Okay, I have 288 columns. If you want to do it properly on the regression, you have to go through the variable one by one and see which one are significant, which one are not. Okay. Of course, you can use the lasso thing to drop some of the variables. And this is your list of variables, and I'm sure you don't want to go through them one by one. Okay. Okay, here comes the magical PCA. Okay, all you need to do is import this library. So it's from sklearn.decomposition. Just decompose it, and then import PCA. By the way, PCA stands for Principal Component Analysis. And here you can specify the number of n. That is the number of columns you want to compress to. Okay, I'll just run it. Okay, after you run it, it becomes a bunch of numbers like this. And you can count that's the number of row, I think. Dot shape. Okay, if you see the shape, previously it was 1,400 rows and 200 columns. Now I just transform the whole thing to 5 columns. Okay, but if you looked at the magnitude of it, now I just screw up all the meaningful things in the data. And now what left is just the variations. Okay, because instead of all the moving dots, I just draw a straight line and create a new column out of it. Okay, so the important point here is now I don't need to deal with 200 columns. I'm left with 5 columns. But I lost all my explanatory power. Okay. But there's one good thing with this. Remember, we don't really like correlation between variables. And in this case, we just remove everything that is correlated and transform them to one thing. Okay. So somehow such process can eliminate a lot of noise and then eliminate a lot of outlier. Okay. So and if you plot out your okay, that's how your new column looks like. Okay, it just doesn't make any sense, and it doesn't tell you anything if you look at this. Yep.
Which one doesn't even need to know the ground?
Sorry.
Like you don't need to know the ground truth. Okay.
Okay, that's a good question. So, okay, in this case, what you do PCA on is just the train X. Okay, you have to preserve your ground truth. It's just you can imagine this to be just some pattern. Okay, but if you have to point those patterns to your ground truth to make the predictions. Okay, so what the computer does is instead of a very long pattern, it just compress to a smaller one. It's a bit like the zip file that you use. You know, zip file is very magical. You want to send someone with a 10 megabyte document, you zip it, it becomes 1 megabyte. This PCA is something like the zip file. You can zip it. Can you unzip it? Yeah, you can unzip it. So you transform it to a zip version, and you can reverse it and make it bigger again.
So you just remove the outlier.
Yeah, you can. I think you can think of it this way. Actually, I'm not 100% sure if I can reverse, but you can definitely zip it. Okay.
But normally, would that change the accuracy of the answer?
I would say pretty much the same. But I guess that's in some degree, if your data is heavily correlated within each other, then it might improve your model. But if your data is not very correlated, you zip it, it means you lost a lot of information. In that way, it just makes your model worse. But what good is if you have a lot of data and your computer takes like 24 hours to run it, you transform them to 4 columns, it would just be like 200 times faster. Okay.
So it's only for like processing speed instead of accuracy.
For easy processing.
For easy processing. Like I think it has to be done case by case. So if you know your data is not heavily correlated, you might not want to do PCA. But if you know your data is actually very heavily intercorrelated, we can just do PCA and transform it. Okay. I think let's say I don't know if you guys do like I don't know stock, like financial data. There are a lot of variables. You can keep on adding variables, but that makes it very easy to overfit your model and make it unable to predict the future. Okay, using PCA, you can sort of combine the many factors you add in, like different kind of news or the index, etc., and make it to point to one general directions. Okay.
But what are those components means after you compress those?
Honestly, it means nothing. It's just some patterns that sort of preserve your variations. Let's say you have a zip file. I send the zip version to you, and you don't unzip it and just look at it. It won't make any sense. But the computer somehow knows they are the same thing. Okay. And the only thing you need to know is the first column has more explanatory power than the second one, and the third one, and the fourth one. So in this case, the first column is always the most important. Okay. And then I think I can skip. Oh. Okay, this is just as an example of the iris datasets. And okay, I won't explain all the codes. And what this does is it compares the iris prediction before and after the PCA. Okay, this one is the PCA of the iris datasets. So PCA, the iris dataset, you have four factors. Okay, if you go to iris.data, okay, you can see there are 4 columns. Okay, now if I want you to plot out this graph, it's going to be very hard because you have 4 dimensions, right? What PCA is good at is you can transform anything to 2 dimensionals. And once it becomes 2 dimensionals, you can easily see how far apart are they. Okay. If you remember at the very start of my my class, I showed you how the football team, how far apart the football teams are, and the closer one means they're more similar. I use PCA to do it. Okay. Okay, I think you shouldn't care about the 3D thing. Okay. How many of you wasn't here in the web scraping class? Okay, so quite a lot of you. So, do you mind if I go through it quickly? Okay, sure. Okay, so web scraping is a very important aspect in data science because there's a lot of data on the internet and you don't want to collect them by hand. Okay, and simply speaking, there are 3 types of web scraping. One is called API, which you pay someone and they just stream you very clean data. Second one is called web scraping, which means you just very tailor-made on one specific site and just scrape it. Okay, just loop the URL and get it. What the most advanced one is called web crawler, which is what Google does. So Google built like a spider, web spider, and you just crawl on every line, every URL it solves. Okay, it usually starts on a front page of a very big website like BBC. And it just goes on every single URL you can find and just go in and to find more URL. Okay, and then what's important is the web scraping part. I'll skip all these. Okay, if you go to this website, pricerunner.co.uk. I think I forgot to record. Okay, pricerunner.co.uk. If you play around with the website's URL, sometimes you can figure out the pattern. Okay, you see, if you manipulate the URL, just go to page 2. You can keep getting the informations. Okay, and if you know about coding, you can do a loop. Okay, you can just basically loop through all the pages. And the way to do it is by using two very simple libraries called Beautiful Soup and Request. Just ignore this one. Okay, if you want to get information from a website, just put the URL and do request get and the websites. Okay, so what this does, it just get the page source of the websites I put in. And if you do r.content, it will just shows you a lot of messy information. And if you wonder what these messy information are, just go back to the page and then go to inspect. Okay, and these are what you just saw. These are called HTML. Okay, and you can somehow see every website is built based on the skeleton. So if you want to extract this value, you just go to here and select the path. Okay, and the highlighted one here means the information is located in this part of the web page. Okay, so the other thing is use the Beautiful Soup to do soup equals okay, after you put use Beautiful Soup, which is parse the page, can make the computer understand the format, and then you can start to do this. Just do soup dot find anything, and if you do this, you can see it just find out the title of the laptop. Okay, and if you do find all, it will just find out all the title of the laptops. Okay, and this is a powerful way to scrape the entire website. So if you have any website that you go every day, you can just turn on a scheduler and ask the computer to keep on getting information. Okay? Sure. Okay, there are three parts in web scraping. First of all is the library. You have two important libraries. One is called request. Okay, what request does is it just grab the source of the websites. Okay, and how it works is just request.get, and then this is the URL you have to key in. So usually you do URL equals, sorry, and then you put the URL in here, and you put .content to find the source. Okay, so now we got all the contents. Okay, let's say I call the content R, and then the next thing you have to do is you have to understand what this piece of thing means. Okay, and you have to do another process called beautiful soup. Basically just add this line. Okay, after you add this line, you can start searching for information on the websites. Okay, let's say you go onto this web page. Maybe you are interested on all the price. Okay, just click on the price, and you can see the price. All the price has the same class, which is this very messy class. Let me try another one. Okay, every price is named after this class. So you can do .find for span class equals this. Okay, so now you extract all the price from the source. Does it make sense? And if you do this, I for I in okay, sorry. If you do this, oh sorry, in soup, then you can just extract all the price in a string. Okay, and imagine you do a loop on this page, and then you extract the price for every single page. Then you can quickly get a lot of information. I'll just show you quickly. Okay, so for I in range 1 to 5, then plus I. Okay, sorry, has to be integer. Okay, once you run the loop like this, basically it just loops through all the URL, and you go to, you just extract all the price on the laptop side. Okay. And then there are some sort of a lot of techniques that you can play around for web scraping. But the powerful thing is, if you build a scraper, you can just loop over the site. So you probably spend 30 minutes to build a scraper, but you can probably get millions of informations out of it. Okay, so the homework for today is this regression homework. So I'm gonna explain it a little bit. Hold on. Okay, that's the one. Okay, this is the homework for the coming weekend. So what I did is I extracted a lot of URL on the Google Sheets. So you have the price and you have the URL for a lot of pages. And if you look through there are around 3,000 URL of laptop specs for different laptops. And if you go on to some of the links, sorry. Okay, and every link looks like this, and you have a lot of product informations. Okay. In here, I've written some functions for you to extract the URL. So if you do this, hold on. Okay, if you do this, if you input the URL of the website, it just shows you a long table of all the information you need for the laptops. Okay, and if you run the functions in here, okay, it will just keep on looping all the URL and extract the laptop informations. Okay, if you think about it, the price of a laptop is based on several factors, like how fast the laptops are, what brand laptops are, and like how big the screen is. And if you looked at a lot of such datasets, okay, everyone looks like this. And what I want you to do is to transform these datasets to a table, and then try to run regressions on it. Okay. But the challenge thing is these are not numbers. Okay, these are a category. So you might have to brainstorm a better way to run regression on things like that. And your train Y is the price. Okay. So any questions for the homework? Alright. So that's it for today. Thank you. Is it too fast or is it okay? Or hard to understand? A little bit confusing. Okay.
Show the for
The for loop, okay. Sorry. For loop. This one. Maybe I'll just send out this Python workbook to you guys.